Hello, this time I want to discuss the partial sum uh, of a geometric sequence. And to start with this, we have a geometric sequence just described in this way, but I want to remind you that geometric sequences follow a special recursive relation, the one that is given in this fashion. You say, uh, for each n greater or equal than 0, the subsequent term of a sequence is a constant factor of the current one. And that constant is the same for each of pair of consecutive terms, right? So we have to remind that. But out of this, what we get is the following. We can provide a formula for for this sequences. They're given by the initial value times c to the power of n. And you can play with this a little bit, but it's fairly easy to obtain it by just unrolling by iterating through the terms of the sequence. I can provide a few. So if you were to start like this, S0, then S1 would be a constant times S0. So C times S0. The next one would be a constant times the previous one, so c times s0, which of course reduces to c squared times s0. Then the next one would be c times c squared times s0, which of course reduces to c cubed times s0, and so on and so on. So it's fairly simple to detect the pattern in this case. Now, what we're interested here is not on that pattern, but on the one that arises from the partial sums. So we are now interested in the partial sums. So what would be that? Well, for instance, if I were to say, well, let me create a little table to help us organize the information. Here we have S of n, and I'm going to call the partial sums P of n. Sensible name. Okay. So, well, let's see. Um, Initially, well, we have S0, and the partial sum is exactly that term. On the next one, right, we have 1. We have, of course, S1, but S1 we know is S0 times C. So now the partial sum is S0 plus S0 times C. Then the next one is going to be S0 times C squared, but that goes for the term of the sequence. Now for the partial sum, it would be S0 plus S0C plus S0C squared. And well, let me just get one more. And we have S0 times C cubed. But now we would have S0 plus S0C plus S0C squared plus S0C cubed. We expect that the pattern is going to continue in this fashion because we're just adding the last, essentially the term. We have sort of a recursive expression, right? For the next one, if we can expand this idea, we would say, well, I will take everything that is here and then just add it to the next term that is going to appear in the sequence. So let's see, maybe rewriting things is going to help us in this case. So I see that among the terms that we have, S0 appears in each of the terms. The same happens for this. The same happens for this. So we may factor it out and obtaining something a little bit more manageable. So this one stays the same. This one is just S0. But this one is S0 times 1 plus c. Well, this one is S0 times 1 plus c squared. Well, this one that we have here becomes S0 times 1 plus c squared plus c cubed. So now I can tell the following. If I was to say things in general, we know by convention that for any real number that we discuss, c to the power of 0 is 1, even for 0 to the 0. Right? You can take it as a convention. That's going to help us a lot. Okay? So now I can say for each n, greater or equal than 0, we have that Pn, the partial sum up to n, is equal to S0 times C0 plus c to the 1 plus blah 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 up to c to the power of n. Right? Just keeping in mind this numbering, right? And this one here, no? The one that is hidden here, and that one there. Okay, of course, we can condense this into a much formal notation where you have this is S0 times the sum ranging from 0 up to n of c to the power of k. I mean, it's just a way of writing it. But what is this sum ultimately? No? Have we seen it before? Well, yes. What I'm going to do is perform a series of polynomial divisions, and with that we will recognize that this is a pattern that we have seen in the past. So so let me start like this. I'm going to divide the polynomial x squared minus 1 by the polynomial x minus 1. I initiate the process, so I multiply it by x. This is just long division, so it would be x squared minus x. What's the remainder in this case? X minus 1. Okay, I can continue. So I multiply everywhere by 1, and I get negative x minus 1. Now stop. I get a 0. 0 is a polynomial of degree less than the one that is indicated here. So we're done. Okay, well, let me continue. I mean, this is just one example. I'm going to increase the degree of this. So I'm going to get x cubed minus 1. I know that this polynomial is divisible by the polynomial x minus 1. Why? Because they both share exactly the same root. Well, they share one of the roots, which is the only one for x minus 1, namely 1. Okay. So let's proceed, just as before. So now we have x squared, we multiply, and we have just the following. X cubed minus x squared, and then we have x squared subtracting minus 1. But then we see something. Whatever I write here is exactly what I wrote here. So basically I'm going to repeat this whole procedure, right, one more time. Well, I don't want to do it, but I want to mention that after making that observation, at some point I'm going to get to 0, and then I'm going to place an x here and a 1 here. And that will be the end of the process. But then imagine that I do it for this polynomial. Let's say that now I have to divide x to the 4th minus 1 by x minus 1. Same thing. This polynomial that I have here, this one, it's divisible by this, because the only root of this one is 1, and this one has 1 as one of its roots. So at some point, the division process will stop with a 0. What needs to be determined is, well, what is that we write here in the quotient? So let's write it. Let's start x cubed. Well, x cubed. Then I multiply and I get x to the 4 minus x cubed. Of course, I'm subtracting. Where I'm left behind is with x to the third minus 1. But once I get that, well, essentially what I have to do is take a copy. A copy of what? A copy of this process, right? But once I copy that process, well, I will copy the entirety of this quotient. But then, well, what that tells me is that I have to add here plus x squared plus x plus 1. And then at some point, I'm going to get to 0 in the remainder. So what is that we're getting here? Well, in general, right, if we were to jump, of course, we're going to make this precise later on. But what we're observing is that if I take any number, right, natural number greater or equal than 0, and then I perform a division, x minus 1, x to the n plus 1 minus 1, well, at some point I'm going to get to 0, and the quotient will have the form x to the n plus x to the n minus 1 plus blah 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 plus x plus 1. In other words, we have this x to the n minus 1 minus 1 plus 1, I'm sorry, plus 1 is equal to x minus 1. I'm just going to interpret the division process, the division algorithm. The sum ranging from 0 up to n of x to the power of k. This is just a simpler way of writing this potentially ambiguous expression. Okay, it seems like we're done because we really wanted to gain access to something like this. The problem is that c is a number, and division cannot be performed on a number that is equal to 0. So we have to make a distinction. Just make sure that you're not dividing by 0. But how do we make sure of that? Well, by noticing that the x that you use cannot be 1. In this case, the c. So recall that c is a number, and division by 0 is undefined. So what does that mean? Well, it means I cannot treat c as a symbol because c is supposed to be interpreted as a number itself. So let's do this. So, okay, we're going to make a division. We're going to consider two cases. Right? One, when c is 1, meaning when this expression will turn out to be 0, so I cannot perform the division. But if that is the case, if c is 1, then this overall becomes 1 plus 1 plus 1 plus 1 plus 1 plus 1. How many times? Well, n plus 1 times. So the overall expression now becomes as 0 times n plus 1 if c is equal to 1. Now, if c is different from 1, well, we are in a safe place. We can make the division. So we have as 0 times c to the power of n plus 1 minus 1 over c minus 1. And this is if c is different from 1. So just a very, very basic example of the usage of this formula, it would be, if I have this sequence, geometric, representing the powers of 2, we know that the nth term of the sequence is simply 2 to the power of n. Let's say that I want to add. Well, I want to know what the partial sums are. Well, the partial sum is going to be given by the initial, of course, in its full format. I'm going to write it as simply, in this case, k equal to 0 up to n of 2 to the power of k. Of course, remember, this is just representing 1 plus 2 plus 4 plus blah 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 plus 2 to the n. But then, based on this formula that we have here, now we can write it in this fashion. This is simply S0, but S0 is 1, and I'm going to write it. So 2 to the power of n plus 1 minus 1 over 2 minus 1, which of course now reduces to 2 to the n plus 1 minus 1. Oh, there we go. Very clean. So, see you next time.